Hey y'all. Today we're going to be delving into how to identify whether something is an acid or a base. We're going to look at both strong acids and bases and weak acids and bases. And we're going to cover both what they look like and how they act. So let's go ahead and get started. Identifying an acid or a base often just comes down to how it behaves. And when it comes to acids and bases behavior, there are really three different categories that we place them in. You're not normally going to be asked to identify which category an acid or a base would be in, but it's really important to understand the three different ways that they behave. And so what I'm going to do is I'm going to talk about the names so that we can have them as an understanding, but in the end, you're really going to be looking at just the behaviors, not the names. The first type of acid and base that we're going to look at are called Bronsted-Lowry acids bases. Bronsted-Lowry acids and bases act as proton donors in the case of acids and proton acceptors in the case of bases. A proton donor would be something that gives up an H+. Remember, a hydrogen atom would have one proton and one electron, and if it's an H+, it loses the electron, which means it's just a proton. So as a proton donor, what's happening is the H is essentially falling off of the molecule as an H+. Proton acceptors, these would be bases, act in the opposite. They accept an H+. Oftentimes that H+ comes off of water molecules in the solution. And so what happens is the base gains an H+, and as a result becomes a different species, and what's left in the water is just an OH-. The second type of acid and base that we're going to look at is called an Arrhenius acid or base. Now, the key to an Arrhenius acid or base is the understanding that it's not just about protons, but instead about the concentrations of two different ions in a solution. Acids, by their nature, will increase the concentration of H+ in a solution. Bases, by their nature, will increase the concentration of OH- in the solution. So again, Bronsted-Lowry and Arrhenius, two different acids or bases based on their behavior. However, they both have the same basic effect. The pH of an acid is going to be lower than 7. The pH of a base is going to be greater than 7. The third type of acid and base that we're going to look at is called a Lewis acid or base. I often think about Lewis acids and bases using a prior knowledge of Lewis structures. Lewis structures we draw using electrons, and a Lewis acid or base is about the electrons. A Lewis acid is going to accept electrons, whereas a Lewis base is going to donate electrons. We're going to see some Lewis acids in bases in this unit. However, they aren't exceptionally common in practice in this class. However, in the real world, they're all over the place. So again, three different types of acids and bases: Bronsted-Lowry, Arrhenius, and Lewis. And as we look at them, the thing to keep in mind is that all three have slightly different behaviors, but the end result is that an acid will always cause the pH of a solution to become less than 7, and a base will cause the pH of a solution of that base to be greater than 7. So here's a table where I simply summarize the effects of the different types of acids and bases. You can see here again how each of the different three behave, which makes them an acid or a base. The way I like to think about acids and bases as it comes to this class is much like a pig. I want you to be able to look at it and tell me it's a pig. And in the idea of an acid or a base, I want you to be able to look at it and simply tell me, is it an acid or a base? You don't need to know much more about it other than whether it's an acid or a base. However, you also need to be able to look at how it behaves to predict whether it's an acid or a base. One other thing to be aware of is that some species, some chemicals, can act as both acids and as bases. These are known as amphoteric species. That means that they can act as both an acid or a base. So let's give an example. Water. Water is a great example. Now, water can give up an H+ ion, and as a result become hydroxide, OH-. That means that water can act as an acid. Water can also accept a hydrogen ion and become H3O+, or the hydronium ion. And as a result, it acts as a base. That's one of the beautiful things about water, and one of the reasons that it's so functional in not just chemistry, but also in life, is because of its amphoteric nature. Water is not the only amphoteric species, though. We might see others throughout the year. So be aware that some things can accept hydrogen ions as a base or donate hydrogen ions as an acid. One other property of acids and bases that you need to know is whether they are strong or weak. A strong acid or a strong base are those species which fully dissociate. That means every single HA, right, which is the general structure of an acid that we put into water, becomes H plus and A minus. There are 7 of these, and you need to memorize them. For instance, hydrochloric acid is a strong acid. When I put hydrochloric acid in water, I get, for every 1 HCl, 1 H plus and 1 Cl minus. For nitric acid, I get 1 H plus and 1 NO3 minus. They fully dissociate. For strong bases, they also fully dissociate. So our 8 strong bases include sodium hydroxide, where when we put it in water, we get Na plus, NOH minus. Also, lithium hydroxide, where we get Li plus, NOH minus. You need to know the 8 strong bases as well. So again, this is a memorization thing. You need to have memorized the 7 strong acids and the 8 strong bases. So if a strong acid's identity is based off of the idea that it fully dissociates, what is a weak acid? Weak acids, by definition, do not fully dissociate. Instead, they go to equilibrium, which is convenient because this is the unit acid-base equilibrium. So when we're looking at weak acids or weak bases, we know that they do somewhat dissociate, they just don't fully dissociate. And the way that they dissociate is just like they would if they were any other acid or base. They just don't go all the way to dissociation. There are some molecules remaining that have the same Lewis structure as the original weak acid or weak base. Others, however, take on that dissociated form. One of the most common types of weak bases are known as nitrogenous bases. These are bases that have nitrogen as an element within the base itself. We might have heard of nitrogenous bases at one point or another during biology class. We're also going to see nitrogenous bases in chemistry, the most common of which is ammonia, NH3. All nitrogenous bases are weak bases. So understanding the 8 strong bases, the 7 strong acids, allows us to then be able to identify which ones are weak just by knowing which ones are strong. If I see a base, I know it's not one of my 8 strong bases, I know it's a weak base. If I see an acid, and I know it's not one of my 7 strong acids, I know it's a weak acid. Let's do a quick identification problem. I want you to tell me which of these would act as a Bronsted-Lowry acid. So the first thing you need to remember is, how does a Bronsted-Lowry acid act? It donates a hydrogen ion, an H+. That means any of the molecules that we are looking at in this problem need to be able to give up an H+ ion. As we look at it, the potassium hydroxide, the first one, it doesn't have a hydrogen it can give up. Instead, when it dissociates into a potassium ion and a hydroxide ion in a 1-to-1 ratio. It's actually one of our 8 strong bases, not an acid. HCN, hydrocyanic acid, is an acid, right? Starts with an H, that tells us it's likely an acid. And as a result, when we look at it, would identify it as a Bronsted-Lowry acid. When it dissociates into an H+ ion and a Cn- ion. So HCN is a Bronsted-Lowry acid. The next ion is the acetate ion. Now, there are hydrogens in it. However, it's important to note that this is an anion. And as an anion, it will happily accept an H+ from the solution. Therefore, this is actually a Bronsted-Lowry base. NaCl is just a salt. There's no H+ or OH- on it, so it's neither an acid nor a base. We're going to talk about why it's not a base later, why it's not an acid later, but in this case, it definitely wouldn't be a Bronsted-Lowry acid or base nonetheless. The final one, hydrofluoric acid, also a Bronsted-Lowry acid. The reason it's a Bronsted-Lowry acid is because when it dissociates into an H+, and an F minus, therefore donating an H plus to the solution, acting as a Bronsted-Lowry acid. All right, so which of these four is a weak base? So if you look at it, we need to remember our 8 strong bases before we can answer this, because all of these are bases. However, some of them are strong, not weak. The first base here, lithium hydroxide, is one of our 8 strong bases, so it's not weak. The second, potassium hydroxide, also a strong base, not weak. Lead 2 hydroxide, however, is a base, but it is weak. It's not one of our 8 strong bases. Barium hydroxide, the last one, also one of our 8 strong bases. So the answer here must be C. All right, here's kind of a tricky one for you. Which of these things is amphoteric? Which means, remember, it can be an acid or a base. Take a look. What do you think? So the answer is B. And the reason it's B is because of the fact that that HSO3 minus can accept an H plus to become H2SO3, sulfurous acid, or it can donate an H plus to become SO3 2 minus, the sulfide ion. Therefore, HSO3 minus is in fact amphoteric. None of the other species could do both, accepting a proton and donating a proton. So that wraps up today's video. Let's do a quick recap. We started by identifying the 3 different types of acids and bases: Bronsted-Lowry, Arrhenius, and Lewis. Remember, in the end, we're going to be able to identify acids and bases mostly based on how they behave. So if we look at an acid and a base, we need to predicate this off of how they act in a solution. So when we look at an acid, it's going to donate a proton, or it's going to accept electrons, or it's going to cause the H plus ion solution in the solution to go up. If we look at a base, it's either going to accept a proton, donate electrons, or cause the hydroxide ion concentration in the solution to go up. In the end, though, the pH of an acid is going to be less than 7. The pH of a base is going to be greater than 7. That's really going to be our biggest determining factor on how something's going to behave. We then talked about amphoteric species that can act as both acids and bases. Normally, we talk about these as it pertains to Bronsted-Lowry, which means they can both donate a hydrogen ion and accept a hydrogen ion. And remember, water is the most common one of those. We then talked about strong acids versus weak acids and strong bases versus weak bases. Remember, you need to memorize the 7 strong acids and you need to memorize the 8 strong bases, because in the end, you'll know if something is a strong acid or a weak acid depending on whether you know the 7 strong acids. You'll know whether something's a strong base or a weak base depending on whether you know the 8 strong bases. Today's video was written, directed, and edited by John Bernard and Lewis Lee. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.